Hello, everyone. Come on in. More people coming in. Oh, I just remembered something. While I'm waiting for more people to come in, I'm going to flip over to our Canvas page, and I completely forgot to open that test back up for people that missed it. So let me do that real quick. Anybody have any questions while everybody's coming in? I'm doing this. Today we're starting chapter 14, or excuse me, chapter 15, wave motion. We finished 14 last time. I would recommend you guys going and looking at, let me see, it's called Best Harmonic Oscillator. It does simple and physical pendulum, and then it says Best Harmonic Oscillator or something like that, and it's from yesterday's D01C class. So you'll find that in on my YouTube channel. That one's a more complete version with basically I worked out all three parts enough where you can see what I was talking about. I even did the initial value conditions, which is you know, quite a bit of algebraic work. So you can see it's a nightmare, but I did that with the first part. And then the other two, I just showed you what the result would be. I'm now making the test that was due on Sunday. I'm going to make it due. It's basically anybody that does it now is going to get a late grade. If you've got extra chances, though, in principle, you could use it to practice, but I wouldn't recommend doing that because you make lower, it's going to, I think it might make the thing show up late. I'm not positive. So I'm going to make it be done by the 20th at 11:59 p.m. The grade book will actually shade it blue or something like that if you do it late. So that'll allow me to take off the points for people that missed it. So I just got that done. Anybody have any questions? Looks like we got 13 people here, so we're good to roll. No questions on anything? I've already opened up those. You have
test 4.
Go ahead now, Matt.
Were you talking about test 4?
Yeah, test 4. I had a student, I think it was in this class. I was pretty certain it was in this class that had missed it on Sunday, just completely forgot about it. And then Monday they asked if they could take it anyways. And I told them they could, but I have to take off a few points for being late. And I'd rather do that anyways than give somebody a 0 for a test just because they made a bonehead mistake. So yeah, that's test 4. Test 5 is actually due tonight. So make sure you'll get that knocked out. And that's why instead of just making it due today or tomorrow, I went ahead and did it till Saturday, just to, you know, not put too much pressure on you to finish 2 tests in the same day. So if anybody missed that test that was due Sunday, then make sure you knock it out by Saturday or the 0 will stick. And anybody that hasn't done test 5 yet need to get that done tonight by midnight. So anything else from anyone? Nope, got another person coming in. All right, so it's now available. It's going to disappear, of course, Saturday 11:59. Test 4 will. Test 5 disappears tonight at 11:59 p.m. So make sure y'all get test 5 done. And I guess we'll go ahead and start into chapter 14. Oh, got another person coming in.
Just as a reminder, test 4 is still under the nothing category.
It is still? I thought I fixed that too. Well, let me fix that too then. Let's see. I thought I just saw it in test, but oh, I know why. I went through the quizzes, which is something y'all don't have access to, but I saw it right next to the other test. That's why I thought it was there. The practice test is there. And then let's see. Mine's showing on my side now, test 4, chapter 8, 9. It's showing under the online test thing. Does anybody else see it? Maybe it disappeared and you haven't opened your browser back up yet. Try going out of that browser page, out of that Canvas page, and then come back in and see if you'll see test 4 right below test 3. That's probably
Professor.
What's that? It is.
Not similar to this problem, but I just want to let you know that the tests so far, I think the newest ones and maybe some earlier ones
Uh-huh.
do not apply to the grade.
Yeah. Somebody told me that. I got to fix that. Thank you for reminding me. Fix test.
Also, the homework question or homework grades from my lab just don't transfer over at all.
Okay, that's something I can do manually, but it's supposed to be doing it automatically. So I will go ahead and make sure I transfer those manually. I'll write that down too.
Yeah, I just went and checked, and test 4 is under the category called nothing.
Okay, so yeah, that would make sense. Do you see the actual link for the test in the module that says online test? Whoever said that, whoever asked that?
Yeah,
Okay.
I clicked on the link and followed it to the grade book, and it says nothing.
Okay, cool. Yeah, that's the whole problem. I just got to change it to online test. I don't know why I've ever put it in nothing, but here we are. So sorry about that, guys. I will fix that. I did make a note this time. Last time I forgot to make a note, so hopefully this will get done in the hour between this class and my next lab. Those of you, by the way, who have lab, I've already opened up the lab for today. Actually, I opened up the lab for today and the next 2 weeks. So y'all can look ahead if you'd like. All right, so don't forget, everybody, I still got people coming in just now. So I just want to remind everybody, make sure you get your test 5 done this evening by 11:59 p.m. or you'll get a 0. Also, if anybody missed test 4, which was due on Sunday, I have reopened it and you have until Saturday at 11:59 p.m. to get that done, but you are going to lose some points because it's not, you did it late. And yeah, that's right. Okay, so let's get started with chapter 14. I want to also remind everybody, I said this earlier, but a lot of people came in since then. We're now up to 18 people in here instead of 12 we had before. So on my YouTube channel, there is one particular video and it's called best, I think it's best simple harmonic motion or excuse me, best damped harmonic motion or something like that. But I'm gonna look at it now. It's called Best Simple and Physical Pendulum and Completed Damped Oscillations. Okay, completed damped harmonic oscillations. Yeah, oscillator. So make sure you do that. Also, I put a cool new banner on my on my YouTube channel. I'm laughing at it right now because every time I see that picture, it cracks me up. It's my little Chihuahua. It's like when he was sleepy, so his eyes are all like this. I put a cigarette hanging outside of his mouth. Anyways, it's kind of funny, but it makes me laugh. So here I am enjoying myself. Anyways, all right. So let me teach you a little bit about waves, and there's some concepts here that are kind of easily figured out, but if you don't, think about it, you're not going to get to. So I want to make sure you understand these concepts. So we're talking about wave motion here, and wave motion really is any repetitive disturbance, something that repeats itself in not only space but also in time, and transports energy from one location to another is really a wave. So that's sort of a definition of a wave. And there turns out to be two types. So if you take, for instance, a slinky and I attach it to that distant wall, and then I shake it like this, what's going to happen is as I pull up like this bit of slinky is going to pull the bit of slinky next to it up. And then when I pull it to the top, it's going to keep pulling it up. But then as I start to pull it back down, it's going to start pulling that next hump down. And then that hump in front of it's going to start doing the same thing. So if I keep doing this, I'm going to get a series of humps that are actually moving this way. And as long as I continue that, then that is basically a wave, and it's called a transverse wave because the particles of the actual media, which in this case is a slinky, is moving this way and this way, whereas the wave is traveling perpendicular to that. So that's a transverse wave. There also is another way. If I pull the slinky really tight and then I do like this to it, what'll happen is as I pull the Twinkie, as I pull, this is a fat man problem. I got nothing else I can say. Okay. So as I pull the slinky this way, it's going to stretch the individual rings of the slinky. Hopefully everybody knows the slinky is just a big spring. It's going to stretch the springs, the circles of the actual slinky, and make what's called a rarefaction. To me, that should be rarefaction, but anyways, it's called a rarefaction. And then as I push back this way, this is going to actually compress the waves. Now that spreaded ones move this way, and now a compressed ones come behind it, and that's called a compaction. So it's compaction and rarefaction. And then I pull back this way, and then I have another spread apart. Right? So it's compaction, rarefaction, rarefaction, compaction, rarefaction, and it will go this way. Now that case, since we're talking about compactions and rarefactions, the spring is actually, particles of it are oscillating parallel to the velocity. In that case, it's called a longitudinal wave. Okay, so those are the main two types of waves, and we have them in 2 dimensions and 3 dimensions, and you can imagine it obviously carries, hopefully you can imagine that it obviously requires particles of some sort to carry a longitudinal wave, because that literally is like something banging us next. And it might not be that obvious that the transverse wave doesn't require media, but it actually doesn't. Okay, so that was one of the problems when we started discovering waves and stuff like that, and electricity and magnetism. People had a problem because they thought in outer space, if the sun is sending us electromagnetic radiation, it can't get to us because waves only travel through a material, what they call a medium, or media being the plural. And in that case, it was bothering them. So they basically invented something called the ether. They assumed that their space was filled with this stuff called ether, and they referred to it as the luminiferous ether, so it could actually put out light. However, when they did experiments that would pretty definitively detect it, they got no results, meaning that literally there was no ether. But a guy by the name of Lorentz, which you've already learned about in the Lorentz transformation equations, saved the idea of the ether by introducing a weird anomaly that the ether would compress itself when it's moving through space, and lo and behold, that's the exact same result you get from Einstein's length contraction and time dilation and all that stuff. In fact, that's what Lorentz transformations were made up by Lorentz for, was to save the ether from that goofy experiment that a really technical experiment, but it was gave such goofy results in terms of showing that everybody was basically wrong. So in that sense, it's goofy. But that's what waves are. They are a repetitive, repeating, if you will, vibrations or oscillations in space and time that carry energy from one place to another. They don't necessarily carry matter, and that might confuse you a little bit, because if you look at ocean waves, you see them crashing and water come hit you and stuff like that. But if you go a little further out where they're actually not breaking, that's really what we mean by waves. Something's going on very specific on a wave when it gets to the shore and it crashes, and it crests over and stuff like that. And your book talks about that, and I'll mention it as well. But the main thing is, you should know the 2 types, longitudinal and transverse. Now, this is a bit of a trick question, but does anyone know what those ocean waves are? Let's say out in the middle of the ocean, or even at least 100 yards offshore, so they're not breaking yet. Are they longitudinal, or are they transverse, or both? Nobody? All right, somebody chatting me. Let's check my chats. Nope, did chat. Okay, so I would expect most people to think that those are transverse waves, because you see, obviously, the water's going like this, right? But if you've actually been out in the ocean beyond the breakers, say, and you were deep enough where you didn't necessarily touch bottom, but you could see the bottom, which is a rarity in North Carolina and Virginia. The ocean's normally not that clear of water, but 3 or 4 times a year it gets that way when we have a light east wind out of the a wind out of the east for several weeks in a row, and then it becomes a light wind. That day it'll be really, really crystal clear. When you get that, what you'll see is, if you're floating on the water, maybe there's a crab down at the bottom that you're looking at, or a skate's eyes, which will startle you, by the way, because the skates tend to shimmy under the water and only their little eyes pop out. And it's kind of weird, because I was snorkeling one day. I went to go get what I thought was a hermit crab, and went to grab it, and it blinked, and it turned out to be a skate's eyes. So that was kind of creepy. But anyways, if you get something like that you can focus on to tell the grains of sand from the other grains of sand, what you'll realize is when a wave is coming to you, you actually get pulled a little bit towards it. And y'all can definitely tell that in the breakers. You can feel the wave sucking you out to sea, right? You can feel it sucking you out to sea, and then you can feel it lifting you up and trying to push you back to shore. So in reality, you're actually tracing out a circle. But notice you're not really making any progress unless you're in the breakers. If you're in the breakers, then of course it's actually pushing you into shore too, or drowning you or whatever, right? So in fact, ocean waves are both longitudinal and transverse. The transverse part's the part that lifts you up and down, but the fact that you're getting pulled out to sea and then pushed back in and pull back at sea and push back in, that's the longitudinal component, okay? So those are some typical waves that you run into. Also, of course, there's earthquake waves. And you can probably find some cool footage on the internet. I've seen some of it where you actually see big planes and they're doing sort of this thing as an earthquake rumbles in a particular area. So the surface of the earth actually gets this transverse wave going across it. And those are called S waves. And they actually don't only do it that way, they also do it through at least the solid parts of the earth. And then they have another wave, which is called a P wave for pressure, or I've heard it's actually supposed to be for primary wave because it tends to travel faster. I'm pretty sure that's true because I think one of my geologist friends told me that that's what they use the P wave for as the primary, not the pressure. But either way, P and S waves. The S waves, because they are shear waves, they can't travel through a liquid. And the reason why is a liquid can only handle a transverse wave at its surface because it's got surface tension. So if you look, there's like, a bunch of molecules along the surface of the top of the ocean or water or pool or whatever. And if you take a molecule down deep inside the pool, this molecule of water has a molecule over here pulling it this way, but this one has it pulling it that way as well. So those cancel out. This is pulling this way, and this one's pulling this way. This one's pulling this way, but this one's pulling this way. So the net force on all of them is zero. So if you tried to make a transverse wave with those particles below the surface, there's no way that this particle is pulling any stronger than the other particles. So it's not going to be able to lift it and make it go this way. So the shear waves can't go through the liquids. They can exist, however, on top of the liquid, because on top of the liquid, you have the three molecules here. And this molecule to the right has a molecule to the left that may cancel out that force. But as soon as they get a disparity in height, then there's more molecules below than there are atop. So you actually get a molecule tending to pull on another molecule at the surface. And that's why this molecule, due to surface tension, can actually lift the molecule next to it. And then that lifts the molecule next to it, and that lifts the molecule next to it, so on and so forth. That's how you get a transverse wave on the surface of water. And the earthquakes, if we watch earthquakes over a long enough time and we model them properly as we learn more and more about what the materials is at each level, what its density is, what its hardness is, all that stuff, you can slowly, and we have, work out exactly where the core becomes liquid. So we know that very precisely all over the whole globe about how deep you have to go before you hit the liquid core. And then by experiments that we've done on the surface of the earth, and basically the Galilean principle that the laws, or the Copernican principle that physics is the same everywhere. We're not special, so we don't have special laws working in this special part of the universe that don't apply other places. So it turns out when you actually take the material, nickel iron composite that's actually at our core, and you subject it to pressures that it's at in the innermost core, it turns out that it goes from solid then to liquid and then to solid again. So we actually have an inner solid core inside the liquid core. That would have been harder to tell, by tracing out the paths of earthquakes, because you lose all the S waves as soon as they get into the liquid. So there's no way to recoup that it's got a solid core inside of that. So that's some information about waves. There's waves on a string, there's a rope or a cable, there's waves on springs, all those different things. And in fact, they all turn out to have a velocity that's proportional to the square root of some force type thingy, or some hardness strength type thingy versus some inertia type thing. So you have to have like a force or strength or hardness factor in the top of the square root, and then below that in the denominator of the square root, you have to have something that's inertial in nature. So something that talks about how heavy it is, how hard it is to accelerate it. So when you actually look at that, you can get some very distinct equations. So I'm going to go ahead and write those down. Your book derives several of them, and I like to do that too, but I think it's more important that you guys know what equations you're expected to know and use, and then see examples. So I'm going to do that now. I've got some more concepts I got to go over, but I first want to make sure you see these. So your book actually takes the time to derive these velocities, but also I want to, clarify some things. So first off, what is a typical wave? Well, you can think of the shape of a sine curve. Okay, and think of that repeating itself forever, because that's really what the sine wave is. It goes on forever. Now, it will be moving with a velocity v, say, and this part right here is called a peak, which evidently I want to spell P-A-E-K. And this part right here is called a trough. I'm going to draw a couple more wavelengths here. And these are all supposed to be identical. Of course, my drawing is not perfect, so I'm sure it's not identical. Now, the amplitude, if you take the equilibrium point or the midline, then the distance down is called the amplitude, as is the distance up. So that is also the amplitude A. Okay. Now, a lot of surfers, they will look at, at the crest of a wave when it's getting ready to roll over, and they'll be down here from the trough, and then they'll call that the wave height. It's not the wave height in terms of physics terms, but it's often used as the wave height in terms of surfers. So many times the surfer will say they're 10-foot waves, when in fact, from a physics standpoint, they're 5-foot amplitude waves. So that's something else to know. Now, as I said, waves repeat themselves in space and time. This is a photograph of one instant in time. So this is one instant in time. And at one instant in time, what we've taken is a picture of basically a wave over a certain space. And therefore, that distance right there is given the Greek symbol lambda. And it's the distance from peak to peak, which is the same as the distance from trough to trough. But in actuality, it's actually the distance from any point to any identical point. So right here is at a height of 0. So you might say, well, this is an identical point, but notice here, the slope is positive and here the slope is negative. So they're not identical points. So if you go all the way to here, you'd also see that this too is one wavelength. And that quantity, of course, is measured in like meters. So the dimensions of wavelength or length are meters. Okay. The amplitude have dimensions. If you're just talking about a water wave, it could be length or meters. But if you're talking about a pressure wave, which is something we deal with. Pressure wave, for instance, sonic boom is a pressure wave. Timothy McVeigh used a pressure wave to destroy the Murrah Federal Building in a horrible way, and for that reason, I think he was sentenced to death, but he definitely went to prison. In that case, the amplitudes actually in units of pascals are newtons per square meter, which is a pressure unit. In electricity and magnetism, the amplitude could be newtons per coulomb, and that's for the electric field. And then the amplitude for the magnetic field would be in Tesla. So there's a lot of different things the amplitude can have units of. But if we're just talking about the height of a wave, then it's normally going to be meters. Okay. The wavelength, like I said, is measured in meters. There's also some other quantities. If you stop thinking about it as an instant in time, what you'd see is that if you look at a finite length of time, or a long time period, what you'd see is that basically, let's say there's a pole in the water, maybe it's one of the pier legs or something like that, and you're standing on that pole, and you have a friend standing over here on this pole, and what you actually see is the wave come in, and you start counting. So this wave is now moved from here. So I'm just sort of following out the path that the wave travels in. Well, my hand got sticky, like this and this. Okay. What's actually going on here in time is this wave is actually moving. So really, when I said an instant in time, I drew that V on it to let you realize that this is also moving in time. But at an instant in time, you wouldn't see any velocity. You just see it move. You just see it sitting still. However, with this one, you actually would see it moving, so that an instant later, we would see this. Okay. And it turns out the distance traveled in a certain time is one wavelength, and that time is called the period. So the period, which equals t, is the time required for the wave, meaning a whole wavelength, to travel a distance of 1 lambda. Okay, so let's say you look at a particular bubble in the water. So there's a little bubble in the water, and you watch that bubble, and then ultimately that bubble goes here, 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 and then it's here again. At that point, you know the time taken is t. Remember, we're looking in time now, so the horizontal axis is no longer distance, it's in time. So the time required for that bubble to go from here to the exact same place on the wave here is 1 period. And there's another characteristic, of course, and that's called the number of cycles per second. So instead of you watching this particular hump go by, what if you stood right here and said, how many humps go by me every second? So F is called the frequency, which you know some of this already because we studied circular motion. F is called the frequency, and it's the number of wavelengths that pass you in a single second. So let me ask you a seemingly somewhat difficult question. If the period of a wave is 4.00 seconds, how many waves pass you in a single second? Anybody know that? The word how many is a little loosely used there, kind of. So let me put that in quotation marks. Does a whole wave pass you in 1 second? Are you guys even there?
I'm thinking.
Okay, could you say that a whole wave should pass you in a single second?
No.
Can you tell me what part of a wave might pass you in a single second? It's moving at constant speed. So let's imagine the wave was 4 feet long. How much of that wave is going to get by you in a single second?
Well, it'd be 1 foot.
1 foot. And 1 foot is what fraction of the 4 foot wavelength?
Quarter.
Yeah. So the answer is 1/4 of a wave.
So it would go from it'd go from like 0 amplitude to max or vice versa.
Exactly. Yep. And that's no coincidence. What I mean by that is the period is actually 1 over the frequency. So we had 4. So the period's 1, or so the period's 1/4. Or they had the period as 4. So the frequency is 1/4. Okay. So for instance, if I said a wave had a period of 0.2 seconds, how many waves pass you in 1 second?
5.
What'd you say? I think you said it right.
5.
Yeah, 5. Yeah, exactly. That's right. Okay, so that's 5 hertz. So that's kind of nice. So now that we know that, we can say, well, with this sentence, it said the period t is the time required for the wave to travel a distance of 1 wavelength. And we know that speed or velocity is equal to distance divided by time. What would you say the velocity of a wave should be then? In terms of lambda, f, t, all that good stuff. Do we know anything about how far it goes in any kind of time period? Period. I'm sorry, clearing my throat. I hope I had an L in there. I'm sure that's what's tripping you up, right? So I left off the L. Can somebody give me a relationship for the velocity of a wave involving lambdas, f's, t's, a's, as we just defined them? Read this sentence. Read this equation.
Wavelength times period.
Almost. Distance
Wavelength
of,
times frequency.
wavelength times frequency would work. Wavelengths divided by time would work as well.
Oh, wavelength
Time would be
divide by
period.
period. Gotcha.
Yeah, exactly. And because the period is 1 over the frequency, or the frequency is 1 over the period, that second expression a student gave us is also correct. So yeah, that's the kindergarten wave equation. Okay. So for instance, if a wave has a wavelength of 5 feet and a frequency of 3 hertz, then that means 3 waves will pass you in a single second. So the velocity of the wave would be 15 meters per second, right? Or 15 feet per second. Sorry about that. So if lambda equals 5 meters and frequency equals 3 hertz, then velocity means 3 waves will pass you every second, and each wave is 5 foot long. So that's 3 hertz times 5 meters, which equals 15 meters per second. Remember, our hertz is, in some sense, a hertz is just 1 over seconds. So that's the unit for frequency, by the way. I should write that up top. You might see old literature, especially if you're in the Navy, that says CPS. cycles per second, or you could just say seconds to the -1 power. That's what that is. The period has units of time, which is seconds. And that's about it. So those are the main characteristics of the wave that you have to know. With that in mind, I'm going to give you some nice, neat equations that give us stuff that we can use. So for instance, we know that the velocity on a string, velocity of a wave on a string is V equals the square root of the tension divided by the mass per unit length. T equals tension, not to be confused with period. That's why sometimes people will use a P for the period. Your book's using F sub T, so you could also use that instead of the letter T for tension if you wanted. And mu is the mass divided by the length of the rope. So if you take 100 foot of rope and divide that mass, take the mass of it and divide that by 100, then you get, let's say, pounds per foot. We normally use, of course, kilograms per meter. So I'll say that the unit for the mu is mass per length, which is kilograms per meter. And this, of course, has units of newtons. Okay, so that's one of the equations we might want to make use of, as is the wave equation, of course, as is all these other little things that we already knew about frequency and wavelength and stuff like that. You know, we still recall that omega is equal to 2 pi times f, and that we already had f equals 1/t, so we can do that already. So we've got all those expressions. Now there's also some other velocities that we can deal with, and your book does do that, by the way, does take the time to derive this one. So I'm just giving you them. You don't necessarily need to know it, but in general, for low amplitude waves going through normal media, V is supposed to be like the square root of an elastic force factor. Now we skipped chapter 12, but if you guys are in engineering, you might already know about these. I'll tell you in a second. Over an inertia factor. So notice the tension force is a force that tends to stretch a rope or a string. So that's what we mean by elastic force factor. So that is consistent with the with the velocity on a string. And that literally means like a guitar string. If you actually know the tension of the guitar string and you know the mass per unit length, which is, you know, the hallmark of the different strings on a guitar, whether it be a bass or whatever, some of them are thick, some of them are thin. And the thicker ones usually have a larger mass per unit length. Therefore, the velocity of that wave that you actually are plucking to make music is this square root of the tension divided by mu. And that's very important because that V is equal to lambda times frequency. And you're setting up a standing wave between two spots. And basically, you're usually playing the fundamental frequency, which is where this length from the nub down here at the bottom to the neck, that length will be half a wavelength. Notice this is half of a sine wave. There's another half. So this is a half a wavelength. So in order for you to get your proper frequency of sound for that string, you have to get the tension right so that the velocity is equal to the frequency you want times this distance over 2, or excuse me, this distance times 2. Okay. So that leads us to some very specific results. This very generic result. If you want to know, for instance, the velocity of a wave going through a rod, so velocity through a rod, then that turns out to be the elastic modulus over the density. Moduli, by the way, since we haven't covered it, moduli equals stress over strain. Now, in this case, it would mean basically a pressure. So you'd say force over area. Notice that stress sounds like pressure. You know, it's got that. That's how I remember it. And then the strain would be the change in length divided by the initial length. That's what a modulus is. This is the modulus specifically for this one, for the E. But for instance, the bulk modulus, B, that's actually the pressure, which is force per unit area divided by delta V over V0. And lo and behold, if you want to know the velocity through a liquid or through a gas, so V fluid, you get the square root of the bulk modulus divided by the density. And for instance, this is why you learn in scuba diving that sound is omnidirectional. Sound is omnidirectional because your brain uses the fact that your ears are separated by some finite distance from one side of your head to the other. And if it picks up a sound in the right ear just a millisecond before the left ear, then it knows it came from your right side. And through experience, it can also recognize whether it's, you know, a little bit more forward or a little bit more backward, stuff like that. So you can actually get that. But when you talk about water going through, say, seawater or fresh water, yes, the density is huge compared to air, because if you're talking about the velocity of sound in air, you're going to use the bulk modulus of the air divided by the density of the air. And the density of water is really a whole lot larger than the density of air. It's 1,000 times larger, in fact. But the modulus turns out to be 1,000,000 times larger for water than it is for air. So you end up getting a velocity that's considerably higher in water. So your ears can't detect the small time difference from getting your right ear to your left ear. The brain can't sort that out. So sound is omnidirectional. Has anybody ever experienced that before? You can still get people's attention with sound. Just the thing is, they're not going to know which direction it's coming from. So they have to sort of spin their head all around, which if you're warning them, you know, hey, a great white looks hungry and angry, it's probably better that they look all around anyways, instead of just look towards you, because you might be trying to get them to look behind them, right? So those are some equations that we can make use of now. This one's just the generic form of all of them. Your book derives some of these. I just want you to use them willy-nilly. So for instance, if you wanted to play a particular note, and let's say a guitar has a string length. So this will be example 1. String length of, let's actually see, I actually have a banjo here, because I'm a banjo playing man. And I should know this off the top of my head, but I don't. So here I am. So it looks like I really didn't want to do centimeter. I really didn't want to do inches, but it looks like that's what I got. Okay. So I'll do inches anyway. So there's that to there. And then that to there is 24. So we'll say 25.6. So string length is 25.6 inches, which I'll convert to centimeters by 1 inch equals 2.54 centimeters. Okay. And I wish to play, I don't know why I grabbed my phone. I wish to play a very specific note. And I actually know the frequencies that my banjo is supposed to play at. And for instance, the D4 chord is supposed to actually, which is the one at the very bottom, it's supposed to play 293.67. 293.6, sorry, hertz. So that's my frequency. Okay. And let's say the mass per unit length of the D4 string, I can Google that really quickly. And I evidently just caused an earthquake. Okay, so it says that, whoa, it's telling me something about string theory. That's not good. Normally I get a little bit better result than that. Mass per unit length of that. Oh, I've actually found it. No, I did not. I found something that does some kind of calculations that I don't want. Ah. Okay, that's way too technical. I didn't want that either. Crap, crap, crap. So the D4 string is really one of the thin ones. Let's just, for argument's sake, let's pretend like the mass per unit length, since that's a lot harder to find than I thought it was. I had a set that I was really planning on using, but I couldn't find it at the last minute when I went to get it, and because I'm getting ready to restring it. But anyways, let's take a figure. Let's say that 1 kilogram would require 300 meters. So mu is equal to 1 kilogram per 300 meters. Now that's not necessarily an accurate figure, but I know it should be pretty darn small, like on the order of 0.00. So if I use that, what I'd like to know is what tension must be the tension. So we know that the velocity is going to be equal to the square root of the tension divided by the mass per unit length. And we know that the velocity is also equal to the wavelength times frequency. So converting that 25.6 inches times 2.54 gives me 65.024 centimeters. Then I know that the wavelength is going to have to be twice that big, because that's the fundamental. Okay. Remember, when you pluck a string, it can be this, that's the fundamental. Then you can pluck it a little harder and it'll be that. That's the first harmonic, or actually this is often called the first harmonic, but that's the fundamental. This is the first overtone. And then you could do another one where it's like this. So the wavelength is 1.5 times the length of the string is 1.5 wavelengths long, so on and so forth. But I'm doing this one where the wavelength equals 2 times the length of the string. Okay, so I can put that in there and that in there, and that's got to be equal to my tension, or that's got to be equal to my velocity. So lo and behold, I can say that the square root of T over mu is equal to L 2L times the frequency. So if I square both sides, I get T over mu is equal to 4L squared F. So T better equal 4L squared F times mu. Let's calculate that. So 4 times 0.65. Notice I said 0.65. I'm using meters. 4 times 0.65 squared times 293.6 squared times 1 divided by 300. And I get a tension of 485 newtons. 5.9 newtons. And that's carrying probably, well, that's actually the right number of sig figs. So there's a typical problem you can do. You can now know, hey, if I want my string to play at a certain tension, I mean a certain frequency, then I can realize that this is going to happen. Okay, that you have to have the right velocity so that that velocity is equal to the fixed wavelength fraction, because remember the wavelength is the is times the frequency is always going to be the velocity, but you've got the length of the string set. That's why you actually put your finger on the actual board at specific sites. With a, for instance, with a violin, you don't have frets, but with a banjo and a guitar, you have frets, so you can actually shorten the length of the length of the wave that you're doing, because always the first fundamental is going to be basically twice as long a wavelength as the string is. So if you shorten that string, you're actually making it a lower wavelength. The velocity is going to stay roughly the same, so the frequency will go higher. So that's why when you fret at the top or no fret at all, it's a low pitch sound or a low frequency sound. But as you get closer and closer to the other end, the plucking end of the guitar or banjo, it gets a higher and higher frequency. So that's enough. We've actually run out of class time, but that's enough for right now. I've got another concept to teach you regarding reflections of waves. And beyond that, I'm going to give you the actual answer in mathematical form, for instance, of the equation for a wave. So just like we had sine omega a times sine, or a times cosine omega t plus phi for a simple harmonic motion, now we're going to have some way of expressing a similar function in space and time, and I've got to give you that result. So and then we'll be done with chapter 15. So that should be next time. You guys are free to go. Don't forget your test tonight. Don't forget to make up the test 4 if you missed it. Keep up with your homeworks. The dates are all proper. I changed them a little bit. They're all good though. Stick around if you have any questions. I'll wait for the last person to leave as usual. Elizabeth, Mary, y'all have any questions? Well, that was my last page. Ran out just in time, I reckon. All right, so we've done all that. Looks like y'all don't have any questions, so I'm going to go ahead and call it a day. See you, folks.